Hi, Professor DeWolf. I'm Ajay, a PhD student at the University of Auckland, and I'm preparing this video to talk about my current research and proposed research directions at the Chair of Circular Engineering and Architecture at ETH. The construction industry continues to suffer from low productivity growth. On the other hand, the building and construction sector contributes to more than one-third of the global emissions. Research studies have shown the potential of using digital technologies to address these issues. However, their use in construction is still in its early stages. With this motivation, my research focuses on developing digital technology-enabled solutions to improve the efficiency and sustainability of the construction industry. Working in this direction, my PhD research specifically focused on addressing the challenges in planning the assembly of precast building projects. Firstly, I prepared a framework for automatically checking the constraints for crane lift operations using heterogeneous data sources such as BIM models, schedules, point clouds, using the semantic web technology. Next, I developed novel methods for automatically generating the optimal assembly schedules for precast buildings using reinforcement learning, a subfield of AI. This research draws inspirations from lean construction principles to develop constraint-free schedules and avoid time-space conflicts and wastes on construction sites. To make contributions across the full life cycle of the building, I see it as a logical step for me to work on the disassembly stage of the buildings, which is a crucial step towards achieving the circularity in the built environment. Traditional practices of manual disassembly planning suffer from heavy reliance on human judgment, which often result in suboptimal workflows. Therefore, researchers have given attention to automated disassembly planning in construction. Previous research on automated disassembly planning lacks consideration of key information aspects such as regulatory requirements and health and safety considerations, as well as their semantic interconnection, which makes it difficult for the data-driven methods such as AI to directly utilize them. Similarly, previous research lagged in adequately handling typical constraints in disassembly, such as workspace and regulatory requirements, and address dynamic situations of deconstruction projects. These limitations hinder the realization of circularity in the buildings through effective disassembly. Addressing these gaps, I intend to answer two research questions. First, I'll identify information requirements for optimal building disassembly planning using literature review and expert interviews, and build frameworks to semantically interconnect them using the semantic web technology. Next, I'll develop lean construction-based dynamic disassembly planning methods based on advanced AI-based techniques such as reinforcement learning. The methods will leverage the formalized information and constraint models to dynamically generate the optimal disassembly schedules based on the latest project information. Thank you for your time.